Hi, I'm Ron Lohman. I'm here with my colleague Manmeet, and we're going to talk about some of the more interesting parts of AI SoCs, and it's really scaling these systems. We see a lot of die that's just packed full of SRAM and processing capabilities, and with the complexity of AI algorithms, sometimes that's not even enough. So they're having to scale these to multiple systems. What kind of trends are you seeing with respect to the IP that Synopsys delivers in these systems?
Where these chips are very SRAM intensive, and these have localized SRAMs very close to their intelligent processing units or IPUs. And again, the same thing is happening. These dies are getting so large, they're almost approaching the maximum reticle size, and customers want to split them down right in the center so that each IPU from different dies can access the SRAM of these other dies.
This helps out with yields, I assume, and it's not just 2 dies. Sometimes we see 4, 8. In some of these systems, I'm seeing more and more racks of these systems with this type of connectivity. So what kind of connectivity is actually connecting these systems together?
They want very high bandwidth per beachfront, which is your edge of the die.
Okay.
They need the lowest possible power. But what's really important when you're splitting the die right in the center is the lowest possible latency and also the lowest possible BER. So essentially 0 BER. We have customers talking about 10 to the power minus 22, which is essentially being now termed as a reliable link, and the lowest possible latency. So that these different CPUs that are now in different dies, you make them look like a single big CPU, and you want to get your power as low as possible. And with these die-to-die interfaces that Synopsys is offering, we're talking here about less than 1 picojoule per bit.
So can you describe to me some of the different markets that these die-to-die, chip-to-chip solutions are satisfying?
These use cases can be split into 2 distinct categories. We have a category that needs to go on an organic substrate, and then we have a category that needs to go on an interposer. Okay. So the organic substrate is serviced by ultra short reach, extra short reach, SerDes type of technologies, serializer, deserializer type of technologies. And this is where we are talking about speeds of 56 gigabits per second NRZ or up to 112 PAM4. And then we have the second piece of this market, which is more HBM derived, or which is more parallel DDR style of interface.
Right, and we see a lot of AI accelerators that are incorporating HBM, so those already have requirements to add the interposers, correct?
Exactly. So that is based on the interposer technologies, and this is where we're talking of speeds which are kind of aligned to HBM speeds of 3.2 gigabits per second or 3200 megabits per second, and in the next couple of years they will be transitioning themselves or going higher to up to 6 point something in the future. There are variants of these standards. As an example, Intel offers what is referred to as AIB, which is about 2 gigabits per second. There's another standard that's coming up that's called BOW, or bunch of wires, and that is kind of all over the place right now as well. These are the standards. The parallel side goes on interposer, and the serial SerDes style, which is ultra short reach, extra short reach SerDes, these go on the organic substrate. There is something in between the organic substrate and the interposer that is coming, which is referred to as InFO, integrated fan out. This is a technology that is even started by TSMC, and this promises higher density than the organic substrate, but it's less complex and a lot cheaper than the interposer.
So one of the things we also see is a lot of different proprietary controllers. It seems like it's the Wild West out there. Is
exactly
that how the market is today?
So it's a very fractured market, right? What a lot of our customers are doing today is something proprietary.
Yeah.
Remember, most of the customers in these cases are owning both sides of the link.
Right.
It's the same die, same homogeneous dies, by the same customer, exactly the same.
Right.
And when I say proprietary, it can be something like a very, very light transport layer controller that they're building. It can be something as simple as interlock-in type of controllers, which is again a very light controller.
Right.
They're looking at different technologies to improve the bit error rate. These are like light forward error correction type of technologies. There's another concept called replay, which is instead of trying to correct the faulty packets, you just retransmit it. Again, the goal is to get to these 5 key carabars that we talked about, which is, you know, the latency and the bit error rate and the reach and the bandwidth and the power. So they're building something very proprietary to meet these 5 key parameters. There's a lot of work happening in the Open Compute platform. And what they're doing is they are essentially saying, just abstract the file layer, get us to something which is standard like a pipe 5.1.1, which is a SerDes style of a pipe interface,
Right.
and do whatever you want to do behind it.
So how does Synopsys address this problem with all the different interconnect and solutions that are out there today?
We have both sides of the puzzle here. So we have our ultra short reach, extra short reach, 112 gig PAM4 PHY, which is also backwards compatible to 56 gig below NRZ mode. And then we also have the parallel side of it, which is compliant to the HPI and the AIB standards. And again, we have super optimized them around the 5 key parameters that I keep talking about, which is the bandwidth, the beachfront, which is the lowest possible power, the lowest possible latency, the lowest bit error rate, and then the reach, how long can you go on the interposer or the organic substrates. On top of that, we are also working with the foundries and the packaging vendors and the bump houses to really, really deeply understand different type of organic substrates, the CoWoS, the integrated fan out, etc. All these different packaging technologies and how they are coming together. And then finally, the digital side of it, right? So again, our goal is to get to the standard pipe 5.1 interface there, which is a SerDes style of pipe interface. And then we have a lot of right pieces of technology to help our customers go from there to however they want to implement their digital piece behind it. And again, it's a lot of collaboration, a lot of interop type of activities that we work with our customers to enable them to get all the way up to their fabric bus.
Right. So a lot of expertise and a lot of coordination with all different types of components. A very interesting engineering problem. So it's some exciting times with a growing market with AI SoCs. So I want to thank you for sharing your expertise. And if you want to learn more, please visit synopsys.com.
Thank you.